First thing is that the area that we are moving around here is this area right in here. It is bounded by the three equations that are given here, the x squared plus 1, the 4 minus 2x, and the x equals 0. When we start, the first one, if we're using vertical rectangles, we're going to be looking for rectangles that are this way. They're going to have a width of dx, so we can start the integral. Oops, I didn't want that. Hold on. I need a regular pen. We can start with the excuse me, with the width of each of these rectangles, which is dx. We're going to then be integrating from, we're moving along from 0 out to this point. This point here is at 1, 2. So the integral we're looking for is going to go from 0 out to 1, and then the height of each one of these rectangles is defined as the distance from the top function minus the distance at the bottom function. So this should be 4 minus 2x minus the bottom function, which is x squared plus 1. The second, if we're using horizontal rectangles, so now instead of vertical rectangles, so we'll kind of get rid of that. We're now going to be looking at this using horizontal rectangles, and what we should notice here is that we're going to end up with needing two integrals, because the first rectangle, if we start from the bottom and work our way up, the first set of rectangles is good until we get to y equals 2, and then we would have a second set of rectangles beyond, between y equals 2 and y equals 4. So that first set of rectangles, the integral is going to be, the integral is going to be from 1 up to 2. Each one of those rectangles is dy tall, and the length is from here back over to the y-axis. And that length is defined by the x-coordinate of this point. We're doing this in terms of y. We're doing an integral in terms of y, so this function in here needs to be written in terms of y. Actually, let me just do this while we're talking about that. Let's take both of these functions, because we're going to need these later. Take both of these functions and rewrite them in terms of, write the function as x equals. We'll write them in terms of y. So the first one is going to be the square root of y minus 1, and the second one is going to be negative 1/2 y minus 4. Right? And for this second one, I've simply taken the second equation and I've solved for x. Right, so now back down to my integral that we're building. So from that point back to that point is going to be right here, the square root of y minus 1. So this is the square root of y minus 1. And then we're going to add to that the second integral, and the second integral goes from 2 all the way up to 4, and it's defined by the blue function here, by the x equals negative 1/2 y minus 4 function. So we're going to do an integral from 2 up to 4, and this is negative 1/2 y minus 4 dy. Now, if we're going to be looking for the solid when we're rotating this around the y-axis, same problem. We're going to end up needing two integrals, but now instead of talking about a horizontal rectangle, what we're talking about is a horizontal disk. Right? So that disk is going to look, let's see if I can kind of sketch this out. That wasn't too good. Attempt number 2. That disk is going to look, that's better, a little bit like that. Right? And each one of these disks is going to be dy tall, and the surface area, the top, the base of that disk, if you will, is going to be defined with pi r squared. The r is comes from here. Right? So you'll notice that this integral we're writing is very much similar to the integral for problem number 2, except now we're writing for the disks. So we're doing the integral from 1 to 2, right? So that's that set of bottom disks. It's going to be pi r squared. We can bring the pi out. I don't care if you leave the pi in the inside of the integral. The radius is going to be the same as the width of the disk that we did right up here. So the radius is going to be square root of y minus 1. That whole quantity is squared, and each disk is going to be dy tall. And then the second part of this, the top disks, those top disks are defined using the blue function, and those disks look like that. Kind of a wobbly disk, my apologies. But the integral for that, again, sort of parallels the integral for our rectangles. We're going to go from 2 up to 4 pi r squared. The pi comes out in front, and then it's minus 1/2 y minus 4, all of that squared dy. Now, if we rotate this around x equals 2, we can actually make a stab at drawing those disks. So let's erase this. And our line we're rotating around, the axis we're rotating around, is right there. And the disks we're going to get, right? So we're going to have one disk that looks like here. This is going to be our set of bottom disks. And then we're going to have our set of top disks up here. Right? And again, we're going to end up with two sets of integrals. Right? So this is going to come into here as the volume, this shape comes into here and then goes out this direction. Right? So when we're all done, we have something that looks like this, and then this is coming in on this side and then going out sort of curvy on that side. Right? And clearly this is not supposed to be there. Sort of like that. Right? That's our shape when we're all done. Right? So it looks, it's kind of this. Alright, so the integral for that, again, it's got two pieces. The first piece, we're taking the integral from 1 to 2 pi r squared. Pi comes out in front. Now the r for this bottom here, the r is the distance from the line we're rotating around, x equals 2, to the function. So the r is going to be this 2 minus whatever this value is. And up here it's going to be the 2 minus whatever the value is out here to the blue function. So we should get 2 minus the red function, which is the square root of y minus 1. And again, we're doing this in the dy direction, so everything gets written in terms of y. So this is squared dy, that's your first integral, plus the second integral is going to go from 2 to 4 pi r squared. The pi is on the outside. The r is going to be the 2 minus that second function. That second function is minus 1/2 y minus 4. That's a 4. And then all of this squared and dy. Alright. Next, if we take this and we rotate our shape around the x-axis, now what we've got is if we're going around the x-axis, what we're going to end up with is a washer, and boom, boom. The washer is going to look something like this. Each one of those washers. So we want to get the radius, the large radius, minus the small radius to get us the area of the washer, and then we multiply it by the width of the washer, which is dx. Right? So this is what it looks like when we do the integral. Right? So we will do again. Here we're going to be integrating from 0 to 1. And let me just bring this back up here and point out, right, that we're only going from the area. It's going from here, the 0, out to 1, which is right here. Right, so we only have washers extending between 0 out to 1. Each one of these washers is dx wide. Right, so maybe we could put down here at the end, put our dx. And everything gets is done with respect to x, bounds 0 to 1, pi r squared, and the radius we have here, right, is going to be 4 minus 2x, that quantity squared, minus x squared plus 1, that quantity squared. Okay. Notice that this is a little bit easier integral. We can do it all in one piece. The next one here, we're taking, instead of rotating along the x-axis, what we're doing is we're rotating around the y equals 1 axis, and what that's going to do for us, let me erase these disks. So no longer are we rotating around the x-axis, we're now rotating around this axis right there, which means that our washers are going to be much smaller. We're going to have smaller washers. They're going to be smaller by 1. Right? So we're going to have the washers that look like that. So then the integral, each one of those radii from the problem up above is going to be 1 smaller than it used to be. So the integral again is going from 0 to 1, pi r squared. Pi ends up on the outside. The inside, we have 4 minus 2x, the original radius. We're shortening it by 1, and that gets squared, minus the interior radius, x squared plus 1. We're shortening that by 1. That gets squared, and this is dx. Right? Now for the fun one. If we take this area and we rotate it around the line y equals 2, watch what happens here. So let me erase this. And what you end up with is, here's your line that you're rotating around, and what's going to happen is the area on the top, right, so this area up here, that's going to get rotated around the x-axis that way at the very same time that the area underneath, the area on the bottom, is getting rotated around, excuse me, not the x-axis, this line, the y equals 2 line. At the same time this area is getting rotated underneath. And if you go a full 360 degrees, this blue area that comes around out of the front of the page and around y equals 2, it's going to end up overlapping this red area that goes towards the back of the page to start with and then comes around to the front. And then if you look carefully at the blue function, there will be a point where the blue function, after we've rotated our area, this area here, 180 degrees around, it'll be down here. And what you should notice is that blue area completely, absolutely covers in the red area. So when we're looking at this integral to figuring out the volume, the red area is irrelevant. It's tucked inside of the rotated blue area. So we just need to find use the integral using disks, and we only need to use the blue function to do this. Right? So this integral that we're looking for, the quote-unquote tricky interval, it's actually quite easy. It's just 0 to 1 pi r squared, and the radius is that blue function, 4 minus 2x, and it is shortened by 2. We're moved up 2 from the x-axis, so minus 2 squared dx. Right? And we're done.